Finally, we are going to see how to use the cryptography techniques that we have already seen to implement the mechanisms that we have already seen. So we're going to use cryptography to implement authentication, digital signatures, digital certificates, and then I'll discuss a little bit of authorization just for completeness sake. So first, authentication. Authentication is a process where two principals verify each other's identities. So if Alice and Bob are communicating with each other, Alice needs to convince herself that Bob is in fact Bob. Bob needs to convince himself that Alice is in fact Alice. There are two flavors of authentication. They are known as direct authentication and indirect authentication. Direct authentication involves direct communication between Alice and Bob. Indirect authentication uses a trusted third-party server. Typically, this is called an authentication server. For instance, it might be a server run by a well-trusted company like VeriSign. We'll discuss indirect authentication second. Let's discuss direct authentication first. So we have two principals, Alice and Bob, who already share a shared key. We call that KAB. And Alice and Bob need to verify that each of them is in fact who they are pretending to be. So Alice needs to convince herself that Bob is Bob, and Bob needs to convince himself that Alice is Alice. So for this, we use a shared key, obviously. So Alice first sends a message to Bob saying, hey, I'm Alice over here. And Bob sends back a random number, which is known as a nonce. A nonce is an accepted terminology and a popular terminology in security protocols. Essentially, Bob generates a nonce for every single session that he has with any principal, and for any single authentication session, a new nonce is generated. Why is this generated? Well, Bob wants to see Alice using the shared key on the nonce. So Alice sends back the value of the nonce but encrypted with the shared key. And since Alice and Bob are the only two with the original shared key KAB, Bob can now verify by using KAB on the same nonce RB that in fact Alice is in fact Alice, because Alice is the only other principal that has access to the shared key KAB. So at this point, Bob is convinced that Alice is in fact Alice. How about the reverse? Well, we do the same thing. So Alice also sends a different nonce, obviously RA, to Bob. Bob encrypts it with the same shared key KAB. And then when Alice receives this, Alice can verify that in fact Bob is Bob. Okay, so this is wonderful, and this particular protocol involves 5 messages, and it involves 5 message transmission times. Now let's look at it. So why do you need 5 messages? Essentially, Alice and Bob are doing the same thing symmetrically, but in opposite directions. Why not send this second nonce RA earlier, say with the first message over here with Alice, and then when Bob sends back its reply, already you can send back the encrypted version of RA. Okay, so why don't we run the more optimized version of this protocol, where RA, Alice's nonce, is sent earlier, and Bob can also send back its reply earlier. This is essentially trying to achieve, this protocol here on the slide is trying to achieve the same thing as on the previous slide, except it's using 3 messages instead of 5, and it involves only 3 message transmission times. Well, not so fast. You have to be really careful about protocols like this. If you try to optimize them, they may be subject to replay attacks. They may be subject to replay attacks even if you don't try to optimize them. So this particular protocol here is vulnerable to the attack known as a replay attack. So Alice may in fact not be Alice. Alice may in fact be Eve, who is pretending to be Alice. And so Eve might start a session saying, hey, I'm Alice, pretending to be Alice, with a new nonce. And then Bob sends back a new nonce RB along with the encrypted version of RA. Okay. Notice that Eve does not have access to the shared key KAB at all. Okay. So Eve has no way to decrypt this message KAB of RA or anything like that, but Eve can use the sequence of bytes or bits. How does Eve do this? Well, Eve starts a second session where Eve says, hey, I'm Alice. And in the second session, she reuses the same nonce RB that was sent by Bob. Okay. So at this point, Bob would send back a new nonce RB2, but also the encrypted version of RB encrypted with KAB. And this sequence of bytes can now be reused by Eve to finish the first session. So Eve now goes back to the first session and replies back to Bob saying, hey, here is the encrypted version of RB. But in fact, Eve did this without ever knowing the shared key KAB. But by simply reusing the sequence of bytes KAB encrypted, used to encrypt RB from the second session, by replaying this message, Eve is able to convince Bob that in fact she is Alice. And at this point, you have a security violation in your system. Okay, so now you've seen what a replay attack looks like. There are a variety of replay attacks. that could happen in secure systems, but essentially it means an attacker is able to replay messages from a different session over here. So the second flavor of authentication is known as indirect authentication. This uses an authentication server denoted as AS over here. Typically this is a trusted server, trusted by everyone. So essentially every principal in the system shares a key directly with the authentication server. You can think of this being either the public-private key or a shared key in between Alice and AS, and also between Bob and AS. So Alice would send a message to the AS saying, hey, I would like to start a session with Bob. The AS sends back a ticket which consists of, the AS actually generates a new shared key for this particular session. This shared key is KAB, but it does not send back the shared key as plain text. Why? Because any attacker would then be able to intercept this message which is sent in plain text. Instead, the AS uses the shared key with Alice to encrypt the shared key itself, KAB, so that Alice is then able to decrypt this first part of the message and get the shared key KAB. And AS also decrypts KAB using AS's shared key with Bob. So Bob is able to decrypt the second part of the shared key, and no one else is able to do that. Okay, so Alice retrieves KAB from the original ticket message, and Alice and Bob are the only ones who will be able to decrypt parts of the ticket message. So Alice is able to decrypt the KAB, but then sends out the rest of the ticket, the second half of the ticket, onto Bob, which can then at that point obtain KAB by decrypting that second part of the ticket. At this point, Alice and Bob both have KAB, and they are the only ones to have access to the shared key KAB because no one else can decrypt parts of this ticket message. And now Alice and Bob can start communicating with each other by using the key KAB. So in this way, Alice and Bob use this third indirect authentication server to share a shared key. Next, we move on to digital signatures. Digital signatures are just like real signatures. When you sign a document, people expect that the signature is authentic, that no one is able to forge your signature, so it's unforgeable. Anyone is able to verify your signature. And finally, it's non-repudiable. Once you have signed something, you cannot withdraw that signature. So to sign a message M, so to say that, hey, I am the one who has signed message M, Alice would encrypt the message with her own private key. Okay, so when we were sending secure messages, we were using public keys to encrypt. Here we use a private key to encrypt the message. So you send the message M along with the encrypted version of the message M encrypted with Alice's private key. Why do we use the private key? Well, this allows anyone in the world to be able to verify by using Alice's public key that in fact this second part of the message, the signature, is in fact Alice's signature. So if you use Alice's public key to decrypt the second part of the message, you should get back the original message M, and in this way you know that Alice is the only one who could have signed this message. If an attacker, for instance, modifies some bytes of the message M, then decrypting the second part will not give you M, and so immediately you'll know that the message has been tampered with. If a different attacker modifies some of the bytes of the encrypted, the second part of the message M, the encrypted version of message M, then decrypting it with Alice's public key will give you some gobbledygook, and that will be different from the message M, and at this point again you'll know that the message has been tampered with. Okay, so this ensures that messages, if they're tampered with, can be discovered quickly. However, as you know, encrypting and decrypting can be fairly costly operations. They might involve a lot of time, as you have already seen before, and if you're going to do this signing business very frequently, this might become a very inefficient operation. To make it more efficient, you can use a one-way hash function first. For instance, secure hash algorithm 1, message digest 5, and you first hash the message, which is typically a fast operation and results in a small output, typically just a few hundreds of bytes. And then you use the encryption with a private key on this hash. Okay? So this ensures that you're using the encryption on a very small sequence of bytes, and so it's very fast. So you don't need to encrypt the entire message. And on the receiving side, when someone is trying to verify the signature, they can also hash the message. Again, the hashing operation is very fast. And then verify that when you use the public key on the second part of the message, you get back the hash of the message. And that ensures that the signature is in fact verified. Finally, we discuss digital certificates. Again, these are just like real certificates. So someone who gives you a certificate saying, hey, you have taken this particular course, C3 course, should also be able to give you such certificates in the digital world. And to do this, again, digital certificates use the concept of digital signatures that you have just seen. Digital certificates typically have a standard format, and they have a transitivity property. So they have a standard format so that principals who receive a certificate are able to verify that the certificate is in fact correct. They have a transitivity property. So if someone is giving you a certificate, that particular someone should be authorized to actually give you the certificate in the first place. And so you can trace the chain backwards, the chain of certificates backwards, and it should end at a trusted authority, which is at the root. So let's see an example of this. So Say Alice opens a bank account at Charlie's bank, and so Alice is given a certificate, a digital certificate that says, hey, this is the account number for user Alice. The account number is 12345, and the certifying authority is Charlie's bank. There's a signature with the certificate, which is essentially you take the name field, the second field over here, the account number field, you mash them together, maybe do an addition or concatenation, whatever, something that is consistent, and then you take a hash of that for compaction, so that it's compact, and then you apply Charlie's private key to derive the signature. This means that anyone receiving the certificate would be able to use Charlie's public key to decrypt this signature and then verify that in fact when you add the name and the account number and hash it using the well-known hash algorithm, you get back the same output. If someone tampers with either the name, the account number, or the signature fields in the certificate, then the certificate will become invalid and people will not be able to use it. So essentially no one can tamper with the certificate itself without affecting its correctness. So Eve, for instance, who might want to insert the name Eve over here would not be able to do that, because then the certificate would become invalid. So here we have shown Alice getting a certificate from Charlie's bank, but Charlie in turn should be given a certificate, for instance, for Charlie's public key. So a certificate that says Charlie's public key is in fact Charlie's public key might be given by the Bankers Federation. So this would be a certificate shown here given to Charlie. Once again, here the name field says Charlie's bank, the public key has the actual public key in there, and the certifying authority is the Bankers Federation. So the Bankers Federation would then sign this message by using the name and the public key over here, along with the Bankers Federation's private key. So anyone receiving this would be able to then verify that in fact the name, public key, and the signature are in fact matching with each other. The Bankers Federation would be given another certificate by VeriSign, a well-trusted authority. The VeriSign would now be at the root of the certificate tree in this particular case. And this particular certificate given by VeriSign to the Bankers Federation would say that the Bankers Federation is being given the public key KFPub, and then it's signed by the VeriSign authority. Everyone trusts VeriSign, we are assuming here, and so everyone is able to verify this certificate. So you have seen that we have constructed a chain where Alice is given a certificate by Charlie, who is in turn given a certificate by the Bankers Federation, who is in turn given a certificate by VeriSign, and so you have essentially a root, a tree, or a DAG, or a directed acyclic graph of certificates that might be given across pairs of individuals, and all the certificates, if you follow them in reverse, if you follow the chains in reverse, should lead to a well-trusted root authority. Finally, for completeness, we discuss authorization. So when you have a pair of principal trying to access a particular object, say trying to write a particular object, how do you know whether that is in fact an authorized operation? So for every pair of principal comma object pairs in the system, you may want to maintain information about whether that principal is allowed to access that object, and if so, in what modes. So some principals may be allowed to only read a particular object. Other principals might be allowed to read as well as write to a given object. This is known as the access control matrix, where every row of the matrix corresponds to a principal and every column corresponds to an object. So the I, jth entry in this matrix is maintaining information about whether the ith principal is allowed to access the jth object, and if so, in what mode. However, this matrix may be very large. There might be thousands of principals and there might be millions of objects in the system. Also, a lot of the entries in the matrix might be empty. It might be a sparse matrix, because in most of the principal comma object pairs, the default entry might be no access, right? So this is a lot of wasted space. Instead, you have two other options, the access control list and capability lists, which are far more compact. The access control list is a per object list of principals who are allowed to access that object, along with the mode of access allowed to each individual. The capability list is kind of the converse, where you maintain a per principal list of files or objects that this particular principal is allowed to access, and the type of access that is allowed for that particular principal. You could also split up the capability list into individual capabilities, where for each principal comma file pair or each principal comma object pair, you maintain information about whether that principal is allowed to access that file or that object. Okay. In this slide, the terms file and object are used interchangeably. Wrapping up our discussion of security, security challenges abound in today's distributed systems, especially because of the large scale of these systems. There are a lot of threats and attacks that are possible on these systems. The confidentiality, integrity, and availability properties are desirable policies or desirable properties, and you use mechanisms to then implement these policies, mechanisms such as encryption and decryption. Also mechanisms such as shared key infrastructures or public-private key infrastructures. And these can be used to implement authentication, signatures, digital certificates. We've also discussed authorization, which is important in secure systems.